Now we can move to the next presentation, which is also the last one before the break. I will present the objectives and key results of Sherpack before we, after the break, delve deeper into the different technologies and results obtained during the project. So before we start, I just wanted to tell a few words about myself. I'm Caroline Locre. I have an engineering degree in paper making. I joined CTP 7 years ago as project leaders in the field of surface treatment of paper and boards, barrier materials, and food contact materials. I'm currently the coordinator of the Sherpack project, as well as participating in several other R&D projects related to surface treatment of paper and boards and development of new food contact materials with specific barrier properties. Let's delve into the Sherpack project now. I will speak today during my presentation about context and motivation that initiated the project before telling you about the concept of the whole project, giving you a few words about the main scientific advances that we reached over the past 3.5 years, as well as key results of the project before moving on to the conclusions. So, I will pass over this maybe a bit quickly because it has been said before today. Paper and board are used already quite a lot in flexible packaging, in rigid packaging for several different applications. We can mention sacks and bags. We can mention specialty paper like greaseproof and so on. We can mention liquid board packaging, which is also made, of course, made of carton board, but not only. It also contains polymers, aluminium, and so on. The main common point between these materials, these packages, is that they all need to protect their contents and ensure their shelf life, as well as needing to ensure the consumer's safety by limiting or even eliminating the migration of substances from the packaging or the outside environment to the food. So this packaging must be adapted to specific requirements of the product and therefore provide very specific barrier properties, which can be very varied and very demanding, as we are going to see just now. Here you can see a few examples about barrier requirements of different products. We won't, of course, detail all this table, but to give you maybe two different examples, here you see highlighted coffee, which is a very demanding food, which we can have a very long shelf life, and which is a product which is very sensitive to water vapor, to oxygen, to the impact of light, to the loss of aromas, because of course we all like our coffee to have aroma when we drink it, and so on. And you can see that, for example, dairy products need varied barrier, lower barrier performance to water vapor and oxygen. Of course, there must be some kind of barrier, but these products are less demanding than coffee, for example, which tells us that these different, many different products that can be found on the market have different requirements, have different shelf life, and therefore the packaging must be adapted to this foodstuff and provide different specifications that will ensure a good shelf life for these products. In terms of packaging today, of course, you know that polymers and specifically plastics are nowadays used still quite a lot in packaging and including fossil-based packaging materials. They have excellent barrier performances, as we all know, but on the other hand, they don't have an excellent environmental ranking. On the opposite, in fact, of paper and board, or I should rather say overall cellulosic materials, which have an excellent environmental ranking, but also, as we know, not very good barrier performances before they are converted. So it is necessary to transform these cellulosic substrates and to apply barrier performances to them before they can be used as plastic materials. And today, the bulk of barrier products that are used on this cellulosic substrate are extruded polymers like polyethylene, polyethylene terephthalate, aluminum, wax, either paraffins, or we also see more and more bio waxes coming onto the market with a small area dedicated to water-based barrier coatings. But the trends that we see today on the market are really to phase out aluminum and to introduce more and more bio-based material into our packaging to as well ensure the recyclability of this material. As Raphael said before as well, to remove fluorinated compounds for this material as well, because they are likely to be banned in the coming years. And to also adapt to the demand of consumer in terms of functionality of the packaging, for example, going to functional single-serving packaging. And this leads us to the Sherpack project, which was developed with all this in mind. So Sherpack, as you saw earlier in this little movie we shared with you, is a European project composed of 6 European partners, which are listed here, as you can see. So 3 research centers, which are CTP in France, Itene in Spain, and ISOF in Italy, as well as 3 industrial partners, so Cargill, Alstom Mungjo, and Beauregard. And the goal of the project is to develop a renewable, biodegradable, and recyclable flexible paper-based packaging material that can be easily converting by heat sealing and folding with an improved stiffness and grip. And I'm going to give you a bit more details on how we plan to achieve that. So as you can see here, the markets we targeted during the project is the market of dry food flexible packaging with, for examples, coffee and tea as foodstuff that could be packaged into the materials we are developing, cereals as well, confectionery could be included also in those kind of market. And thanks to the 2 proof of concept that we worked on during the project, one which is composed of, as you can see here in this slide, paper substrate with barrier to contaminants and oxygen and grease brought by the wet lamination technology, and another barrier which is heat sealable layer and barrier to liquid water and water vapor brought through water emulsion. This brings us to a first proof of concept material with good barrier performances. And the second proof of concept adds to the first one the printing of a grid, which will bring high stiffness to the material while allowing to reduce its overall weight. And of course, we are targeting a material that is mainly bio-based, as you can see on the left. So this proof of concept, of course, all the partners of the project contributed to its development, which with, as you can see here, CTP and Beauregard participating to the development of this wet lamination of MFC layer, which is a patented technology, and provides a barrier to oxygen and to contaminants. You will get more details later about this development, but I can say here that several grades of MFC were tested during the project, for example. The barrier layer on the internal side of the packaging, which is water-based barrier coating, was developed by ISOF, Itene, and Cargill, with CTP working on the coating. And this emulsion has a patent pending. And on the other side of the material, so on the external side of the packaging, we have this reinforcement grid, which I spoke in the previous slide, which allows to increase the grip of the packaging and its specific stiffness while decreasing its overall packaging weight. And this grid was worked on by Cargill and CTP and Borgard with a patent pending in the project. And of course, in the middle of all this, we have a cellulosic substrate, which is a one-side coated flexible paper for packaging, which is a commercial product from Alshon Mungjo, and which was investigated and deemed as being a really good substrate for this kind of application. And so these two proof of concepts were developed and produced at lab scale over the lifetime of the project. I mentioned the partners of the project, and you can see here that the partners are covering only part of the value chain, from the raw material to the development, production, converting of the packaging material, and going then to the end of life with recycling and composting. But there was missing in the middle the part about filling, storage, use of the material, and which this is why we included in this project a very important advisory group composed of brand owners, which gave us excellent advice on these topics of for example, use and storage. So now I would like to talk about the main scientific advances that we made during the project. A very important point is that we designed our material at all times with the food contact compliance in mind, because of course the idea is to ensure consumer safety, and therefore the paper substrate we selected was compliant with food contact regulation. The polysaccharide grid was compliant with food contact regulation in Europe. The MFC layer is compliant with BFR 36 recommendation. And the waterborne emulsion that was developed was of course developed with food contact compliance in mind, and this means that absolutely no forbidden substances or additives were used in this development, such for example as chlorinated solvent, which were banned from the beginning, even though they are commonly used in in emulsion processes. Here, the point was to develop a safe material, and this is exactly what we did. To give you a few words about the grid, so I mentioned that we printed polysaccharide grids on the paper surface to improve the bending stiffness. These grids and the partners of the project will tell you much more about it in a further presentation. But these grids were designed having in mind auxetic materials and using specific designs on this grid with specific polysaccharides, a specific pattern, specific covering range, in order to significantly improve the bending performance. And here you can see that what we achieved is multiplying by 3 this performance with a 50% covering ratio. while starch was the best of the polysaccharides that were tested during the project. I also mentioned end of life, and here my colleagues will also tell you more in a later presentation, but just to tell you that we investigated several strategies during the project for the end of life. Recycling was investigated. Sorry. Composting is undergoing investigation, but with very good preliminary results, and as well as energy valorization. And of course, more than the end of life, the life cycle assessment of the whole product has been worked on. It is still ongoing, but preliminary results will be shared later. And what I can say here briefly is that the carbon footprint of our proof of concept are very, very close to the fossil-based counterpart materials. Now to move on to the key results of the project. Here you can see on this slide the barrier performance that were achieved on the proof of concept during the project. What I can say is, so I mentioned that we have two different proof of concept, one with the grid and one without the grid. And we obtained very similar results in terms of barrier performances between these two proof of concept, which is excellent because it means that we don't see any impact of this grid printing at the surface of the paper on the barrier performances. We conserve them. So as we can see on this slide, we have excellent water, grease, and oxygen barriers. Water and grease barrier were measured using the COB method, as you can see here, and OTR was measured at 23 degrees and 50% relative humidity. So as you can see here, we have very performant material for these properties. However, the water vapor barrier still needs improvement before it reaches a good level. I would like to make a quick focus on the mineral oil barrier, because this is the only time we will speak about this today, although it is a very important point in the development of the packaging to ensure consumer safety and reduce the migration of substances such as mineral oil from the packaging or from the environment to the food. And here you can see that in red on this graph, we have the migration of mineral oil when there is no barrier on the substrate, which was of course not designed to be a barrier, it's a substrate. And in green, we have the performance of the substrate when an MFC barrier was added to it. And what we can see here is that even at an 8 gram per square meter layer of MFC, we reach a barrier performance which allows to go below the migration limit of 0.5 milligram per kilo of MOA, which is an excellent result. And this barrier becomes better and better as we increase the coat weight, which was expected, I have to say, and we can reach a reduction of 98% and more of the migration of mineral oil by applying this barrier layer. To give you a bit more details about this, while not remaining too long on this, because you will find detail in future scientific articles on the topic. But the climatic conditions of the migration were evaluated on the mineral oil barrier performance. And what we can say is that, as expected, temperature has a significant impact on the migration of this mineral oil, especially on the heavier fractions with longer carbon chains of these materials, while the humidity affects much less the migration. which is good news since cellulosic materials can be sensitive to humidity. But here we see that it doesn't affect the migration of these substances that much. And the lighter mineral oil fraction are affected by the humidity. To finish with the key results, I will say a few words about the heat sealability of the material and its printability. The heat sealability was, so it was tested on a Brugger press, and you can see here that we reached seal strength of about 1 Newton for sealing for 1 second at 200 degrees, which is good, but still could be improved maybe through increasing, for example, the thickness of the coating layer. The printability on the other end is excellent on the first proof of concept. So if you remember the proof of concept without the grid, flexography and screen printing show very good printability, while gravure is under investigation. As for the proof of concept number 2, which is the proof of concept with the grid, then the grid makes this material unprintable in its final state, but it can be easily imagined to overprinting strategies. For example, printing before applying the grid could be perfectly envisioned. And now I'm reaching the conclusion of this presentation. And here I just want, to do 2 things. First, to give you a few key numbers about the Sherpack project. So during the project, we were able to apply for 2 new patents. We, and I want to thank all of you today, reached 300 workshop participants over 2 different workshops. We, by the end of the project, will have 4 different scientific articles on different topics. Our videos were seen quite a few times on YouTube, and we were able to make quite a lot of general communication and dissemination to the public. And the last number is, of course, the COVID-19. And here I want to point out that and thank all the participants and especially the partners of the project, which continued to work during this pandemic in order to complete the project on time. So thank you very much. And before we part, I want to show you the second part of this little animated movie you saw earlier, which resumes the key results of the project. So I will show you this immediately.
In 2017, 6 European partners joined forces and knowledge to imagine an innovative paper-based flexible packaging material. A renewable, recyclable and biodegradable material that fully answers today's expectations of functionality and sustainability. In 2020, their work has given life to Sherpack, a new material combining 3 innovative technologies that will be scaled up for industrial use in the future. The wet lamination of a fine layer of cellulose fibrils on a paper substrate, the formulation and coating of a waterborne biopolymer emulsion, and finally, the formulation and printing of a polysaccharides grid. The cellulose fibrils layer confers excellent grease, oxygen, and mineral oil barrier properties to the material. An innovative emulsion process was developed for the biopolymer, which can now be applied on the substrate using a conventional water-based coating process. The water vapor barrier and heat sealability of the material have been improved and shall be enhanced in the future. The third technology increases significantly the stiffness of the packaging while lowering its weight. The performances achieved thanks to this grid largely exceed expectations. Moreover, Sherpack is fully compatible with flexographic printing, often used in the packaging sector. Bio-based, recyclable, and mainly biodegradable and compostable, Sherpack demonstrates excellent performances for food packaging and complies with food contact materials regulations in Europe, ensuring consumers' safety. Nowadays, the food packaging market represents 3.7 billion euros in Europe in 2020 and faces major environmental challenges. In a sector where plastic films and aluminium reign, Sherpack could well offer a sustainable alternative for the packaging of the future. Vector of the circular economy, Sherpack is the product of a pooled European know-how and paves the way for a new generation of materials.